Ladies and gentlemen, please let me introduce you to the quality human being that is Nathan Oakley.
Now I didn't actually go and proactively watch this crap. One of my own presented it to me. Irritating that I might find that, yeah? They go, oh, look at Ruhif, the lying shit. Look at what he's doing, the lying turd. Yeah, don't you just hope he gets cancer, the lying bastard? Well, there he is, lying like a fucker to all of his audience.
You stay classy, Nathan, you stay classy. Yeah, so I had quite a few little birdies tell me that I was the star of the show back in Flat Earth Debate number 1541, where I assume it was probably 10th Man or maybe Adam Meakin that forced him to watch my sextant video. Alright, let's get into it.
You better fear me, anti-flat earthers. Ruhif, you are thick.
Yeah, I don't know, dude. Word on the street is that you're the one with a bit of junk in the trunk. Anyway, let's continue.
Ruhif, yeah, you want to put one of your little comments below about how you're acquiring the geometry to derive R from a physical geometric sphere edge horizon when you've spent 23 months telling us how refracted it is? You want to explain that to my audience, maybe in a little response video, you abject coward?
Sure, particularly because you asked so nicely, I'll explain it to you in a minute. But you all know that we cringe when you call someone a coward, right? I mean, you would be utterly destroyed without your mute button. And dude, everyone knows it. I'm just embarrassed for you, man. Anyway, offer is on the table. It's always there to meet on a neutral platform where you can actually have your little tootsie toes held to the fire. Anyway, to answer your question about how we use geometry on a refracted horizon. So Mick West came along with his curve calculator many years ago, and it wasn't until something like 2018 when he added calculations to account for refraction. So now the calculator presents two sets of results, one with refraction and one he's just called the geometric results. Now I don't think Mick took any more than a couple of seconds to give names to these, but I'm sure if he thought about the infinite stupidity of flat earthers, he would have realized that at some point flurfs are going to go, hey, if this one is called the geometric, then that means that you can't do geometry on the other one. So that's where I think this whole you can't do geometry on a refracted horizon thing comes from. So now, when someone talks about the geometric horizon, I immediately ask them, by geometric horizon, do you really mean the unrefracted horizon? And at that point, they usually say yes, and that's what they're referring to. And then I tell them, I don't give a shit where the unrefracted horizon is. We have an atmosphere and refraction is a thing. So the second point that Nathan brings up is how do we do geometry if our line of sight is curved? Now I realize that Nathan is probably not a regular viewer on my channel, so I assume he missed out on the little demonstration I gave in my latest response to JTOL and Media 1, where I built something in GeoGebra that demonstrates how it's done. So I'll leave a link in the description to both the JTOL video with a timestamp, as well as a link to GeoGebra. Alright, so on screen I've got the Earth, which is represented by the blue circle, which you can see on the x-axis has a radius of 6371 kilometers. The red curve is the curved path of light, and as you can see about halfway down on the left, this has a radius of curvature of around 45,000 kilometers. And that's approximately how much light will bend in typical atmospheric conditions, and that's regardless of the shape of the Earth. Now, doing geometry with two curved lines is pretty difficult. I mean, it can be done, so you can find the point at which a curved light ray touches the Earth and determines the horizon, but like I said, it's pretty painful. It would be a whole lot easier if we were dealing with one straight line and only one curve. So what we're going to do is flatten out this curved line of sight until it's a straight line, but the key factor here is that we want to maintain the relative curvature between the light ray and the curvature of the Earth. So when we start flattening out the light ray, we also have to start flattening out the Earth. So you'll see that as I drag this slider across, both the light ray and the Earth start to flatten out in proportion. And the net effect of that is that we end up with perfectly straight light rays and an Earth with a slightly larger radius. So if anyone is interested in the math behind this, here it is on screen. So remember, we're trying to maintain the relative curvature between the two curves. So let's start on the left side. To get the relative difference in the curvature, we start with the curvature of the Earth which is 1 over the radius, which we've called r, and take away the curvature of the light ray, which is 1 over its radius, which we've called L. So we do that and we get some number. And on the right hand side, you'll notice that we've intentionally given the light ray a curvature of 0, which means that it's a straight line. But we need the right hand side to equal the left hand side. So whatever number we got on the left hand side, we're going to have to figure out what that 1 over mr term is. And again, if you passed 8th grade algebra, you'll be able to rearrange that formula in terms of m. So let's try plugging some numbers in and try to get a radius multiplier. Now obviously we're going to plug in 6371 for the radius of the Earth, but for the radius of the light ray, you're probably wondering where I pulled that 40-something thousand number from before. Well, that number comes directly from measuring the vertical density gradient in the atmosphere. So this part has absolutely nothing to do with the shape of the Earth. It's purely a vertical gradient. Now, if you've seen any of my previous refraction videos, you might remember that at the surface, the refractive index of air is around 1.000277. And if you go up 1 kilometer in elevation, the air gets a little less dense, and the refractive index might be something like 1.000254. Now obviously these numbers change with atmospheric conditions, so either of them could be higher or lower, and therefore refraction could be weaker or stronger. Now to get the curvature of the light ray itself, we need to get the change in refractive index per kilometer, so just take one from the other to get the gradient, which in this case is 0.000023. And then to get the curvature of the light ray, we just take the reciprocal of that gradient, and that comes out to 43,478 kilometers. And that's what we plug into the formula. And that we get a value of 1.1717. And that means if we want to straighten out that light ray and maintain the relative curvature between the light ray and the Earth, we need a radius that is 1.17 times bigger than the actual radius. And that is where 7 over 6r comes from. And by making the radius bigger, this is how you get a straight line tangent to a sphere when the light is taking a curved path in reality. So making that light ray straight is literally the entire reason for 7 over 6r. I repeat, the whole reason for the existence of 7 over 6r is to make that curved line of sight straight. So I hope that answers your question, Nathan. I'm sure it does, and I'm also sure that once you realize it does, then you'll retreat back to your usual shtick of globers presupposing a globe. Well, I hate to break it to you, champ, but you presuppose the globe as well. Every time you use the black swan modus tollens argument, if the Earth is a sphere with radius 3959 miles, you're doing exactly the same thing we're doing, presupposing the globe for the sake of the argument. Every time you use a curve calculator, you're presupposing the globe again. Like, I won't make this video any longer than it needs to be, so again I'll leave a time-stamped link in the description to my previous video where I discussed this. Alright, onto this business of a curved adjacent.
You haven't got a curved adjacent and you never will. You need straight, flat baselines to measure any angle, anything, ever.
Right, so as best as I can tell, apparently the fact that you can measure an angle at all when light bends is somehow proof of flat Earth. Right, so for those of us who aren't simpletons, we accept that light bends and we just incorporate it into our mathematics, just like 7 over 6r does. It really isn't that difficult. Now, to be fair, Nathan probably hasn't watched my response to Sleeping Warrior, so to reiterate, when we are measuring light that takes a curved path, all we are measuring is the angle at which it enters the lens. If you want to hear me say basically the same thing to Sleeping Warrior, QE, and Mitchell from Australia, I'll leave a time-stamped link in the description. The other possibility for this idea of a curved adjacent is the arc between the observer and the GP of a star. So for some reason, you Muppets think that there needs to be a right-angled triangle to calculate the distance to the GP of the star. But you've been told a million times that we don't even need a triangle to work out the distance to the GP. All we need to know is that it's 69.1 miles per degree from the zenith. And to use that formula, you're gonna need R for that. So again, I'll leave a link in the description to where I covered this in my previous video. But sure, you guys go on ahead with your right angle triangle, but please actually do the trig. I would love to see how it works out. And just while we're on the topic of measuring the angle to the stars, did I hear you right when you said you need a straight line to measure the angle to anything? If that's the case, then why is there a table in the almanac specifically to correct for refraction? I mean, could it be that your line of sight to the star is curved as well? So I think it seems like your right angled triangle has a curved hypotenuse, my friend. Anyway, it's been a pleasure, Nathan. Let me know if you want to venture outside your safe space, and we'll see if we can arrange something. Mwah. Love you, pumpkin.